So while we're talking about temperature and pressure, it's important for us to define a specific term known as vapor pressure. And vapor pressure itself is perhaps best illustrated by this following example. If we take a flask, shown here, and we evacuate everything out of it, we take all of the air out, so there's actually no molecules left in there. It's completely empty. The pressure inside is zero because there's no molecules inside the flask. And then if we add some liquid ethanol to the flask, we'll have liquid ethanol at the bottom. But among the liquid molecules, some of them will have various degrees of kinetic energy, and some of them will actually have enough energy to escape the liquid phase when they hit the surface and enter into the gas phase. And so we will have then an equilibrium that begins to establish between the gas phase molecules that sit above the liquid phase and then the liquid phase itself. And some molecules, because the kinetic energy for the whole system should remain constant unless the temperature is changing, then some molecules from the liquid will enter into the gas phase and some from the gas phase will eventually collide back with the liquid phase and re-enter it until we get to this point where we come to equilibrium, where we have molecules exiting and entering at the same rate. And when we do that, the pressure that's exerted by the gas phase that exists above the liquid phase, that pressure is known as the vapor pressure. So when at equilibrium, the pressure exerted by the vapor phase of a solid or liquid, this can occur for solids, although much more rare, it's generally very, very small. This is known as the vapor pressure. Now, vapor pressure is important because we can directly relate it to the kinetic energy, which is directly related to the temperature. So in any liquid phase, there's always a distribution of molecular speeds, even if the average kinetic energy is at some particular value. Now, some small fraction illustrated here in sort of shaded in will have the minimum kinetic energy that's required to escape the surface and thus enter into the gas phase and become part of the phase that exerts the vapor pressure. What we'll notice is that as you increase the temperature of the solution or the system, kinetic energy is directly proportional to temperature. So as you increase the temperature, you shift this curve to give more proportion of molecules the minimum kinetic energy required to escape the liquid phase and become part of the vapor and thus contribute to the vapor pressure. So the higher the temperature, the greater the vapor pressure for any liquid. Now, in an open system, if you take a glass of water and you set it on the counter and you just leave it for several days, you'll notice that eventually the water level decreases until it dries up entirely. And that's because in an open system, like your room or your kitchen, equilibrium is never established. The molecules, when they enter the gas phase, they don't stay over the liquid, they just leave. And so then there's no return of molecules to the liquid phase. And presuming that the temperature in the room remains constant, the liquid molecules are always at the same average kinetic energy, even when molecules leave, and so more of them will be shifted eventually to have the kinetic energy required to exit the surface, and eventually all of them exit the liquid phase into the gas phase, and you get full evaporation. Now, the greater the vapor pressure, the faster a substance evaporates. If we have more in the gas phase, then more of it will leave at a greater pace, and the evaporation will occur quicker. Now, volatile, there's a particular term for this. So volatile is a term for a liquid that evaporates readily at room temperature. And volatility, which is to measure how rapidly something evaporates, and boiling point are inversely proportional. So if you have a high boiling point, then the volatility is low, and that's because high boiling point indicates that a high boiling point has a lower vapor pressure. If we're just saying room temperature and we've got 3 different liquids, the higher boiling point one will have the lower vapor pressure and thus the lower volatility. Now let's relate this here a little bit more specifically. So to the boiling point, between vapor pressure and the boiling point and that relationship. So the boiling point itself is actually defined as the temperature at which the vapor pressure above the liquid is equal to the atmospheric pressure. When those two things occur, when we've heated it enough to get to the point where the vapor pressure, the amount above the liquid in the gas phase, has a pressure that's equal to the external atmospheric pressure, that's when we have our boiling point. And the normal boiling point, we'll define here, we can set a normal boiling point for all liquids. That is the boiling point at 1 atmosphere, or 760 torr. What we can show is this sort of curve here between vapor pressure and temperature. And if we set 760 here to be atmospheric pressure, so the normal atmospheric pressure, 1 atmosphere, 760 torr, what we'll notice is that at 0 degrees Celsius, we'll have varying degrees of vapor pressure depending on the liquid. For water, your vapor pressure is essentially 0 at 0 degrees Celsius because water is in the solid form. So it'd be very, very, very few molecules that it would have the energy to escape, not just the liquid, but the solid form into the gas. And then as we heat the system, as we increase the temperature to 20 degrees, 40 degrees, 60 degrees, you'll notice that the proportion of molecules that are able to escape increases with that increasing temperature and kinetic energy, and thus the vapor pressure increases. And this trend continues all the way until we hit the point where the vapor pressure is now equal to 760 torr. This occurs at 100 degrees Celsius, and this is known as the boiling point. For ethyl alcohol, however, the vapor pressure for that liquid reaches atmospheric pressure at only 78.3 degrees Celsius, and thus this is its normal boiling point. Diethyl ether is very volatile, and it reaches, you can see that even at 0, it has fairly significant vapor pressure, and so it reaches 760 torr at only 34.6 degrees Celsius. And so this is the relationship then between vapor pressure and boiling point. So with all of that information there, let's quickly just work a problem related to vapor pressure and boiling points. So a city with an altitude of 5,000 feet above sea level has a barometric pressure of 633 torr. So that's the atmospheric pressure at that city. So to what temperature would you need to heat water to boil it in that city? So rather than being at 1 atmosphere, we are told that the external atmosphere is 633 torr, so not 760, but 633. So we simply need to find the point on the curve where the vapor pressure of water equals 633 torr. It's a little bit of an estimation here. And then we'll go from that point and find the corresponding temperature. So water is the blue curve, 633 for its vapor over pressure is roughly here, something along those lines. And we can carry that across and say that we hit the vapor pressure curve for water at approximately this point. So if we then track this point downwards until we cross the temperature axis, what we'll see here is that it's a little bit of a rough estimation, but we would say maybe approximately 90 degrees Celsius would be necessary to reach the point where the vapor pressure would equal the external pressure of 633 torr. And so the new boiling point for water at 5,000 feet above sea level would only be 90 degrees Celsius. And this is how we relate vapor pressure to boiling point, and also talk about volatility and evaporation. All of those concepts are related to this phase change kind of in this way that relates temperature and kinetic energy.